Here we'll do the walkthrough answers for progress test B, so I'm going to deal with the structured answers. So in the first one we've got a reaction between titanium 4 chloride, which means that we've got 4 chlorines for the titanium with magnesium, and we're going to make magnesium chloride and titanium, and that just needs balancing up. So we can see that we need 2 magnesium chlorides to balance the chlorines, and that means we need 2 magnesiums as well. In terms of the role of the magnesium in this reaction, we can see the magnesium changing oxidation state, so it's going from 0 to +2, so the magnesium is being oxidized, so it is the reducing agent. For the calculation, we'll start by working out the moles of water. So 210 milligrams is 0.21 grams, and that gives us 0.0117 moles of water, and we can see that's equal to the moles of magnesium hydroxide in stage 1, which means that the mass of magnesium hydroxide is that moles times by its MR, which gives us 0.68 grams. So the amount of magnesium oxide in mass must be the original mass take away the amount of magnesium hydroxide, which is 2.52. So the percentage of magnesium oxide is 2.52 out of the original mass times by 100, which comes out to be 78.7%. In question 2, the first stage is after an initiation stage. It's slightly more complicated. What we're wanting to do is to give ourselves a chlorine radical, so we want to break one of the carbon chlorine bonds. So I think I would have done this by drawing out the molecule itself and then drawing it out again, but with that carbon chlorine bond now being broken, and each of those will be a radical. Now we've got the 2 equations showing how chlorine radicals catalyse the decomposition of ozone. So straight from the notes, so that's the first one, and that's the second. Good way just to check that things have worked out. Just have a look at what you're left with overall, so we can see that the chlorine radical is a catalyst, and the ClO radical is an intermediate, and what we should be left with overall is 2 ozones making 3 oxygens. So if you've got that, then you've done it right. The next question about distinguishing tests. So in this first one, I would be drawn to the fact that we've got a solution with barium ions in there. So to test for that, I would be wanting to use sulfate ions. We can't just put sulfate ions as a reagent, so we might have gone for sulfuric acid. I'll just put sodium sulfate down as mine, and then with the sodium chloride there'll be no change, but for the barium chloride that's where we'll get our white precipitate. For the next one, I think I'd probably use the fact that we've got a carbonate present, so I think I'd probably choose to use an acid here, so a named acid such as hydrochloric acid, and I would get no change with my sodium chloride, but effervescence or fizzing with my carbonate. You might hear of chosen to use silver nitrate to test for the chloride ions. If you did use silver nitrate, then make sure that you'd say acidified silver nitrate, and there would be a white precipitate with the sodium chloride, but just be careful here, so you would get effervescence because it was acidified with the sodium carbonate. Question 4, another distinguishing reaction. A couple of alcohols, so it's worth just having a look at the structures. So there on the left I've drawn 2-methyl-butan-1-ol. We can see that's a primary alcohol, whereas the one on the right, the 2-methyl-butan-2-ol, that's our tertiary. So immediately I'm thinking that tertiaries can't be oxidized. So this is how I'm going to distinguish between the two. So I'm going to use acidified dichromate as my reagent. So in an exam, probably safest to write out so potassium dichromate along with my sulfuric acid. For my primary alcohol, this is going to go from orange to green, but it will remain orange or no change for my tertiary alcohol. Naming isomer X, so here's the functional group, so we can see we've got a ketone, and it's cyclic as well, so cyclo, and we've got 5 in the ring, so cyclopentanone, no numbers required. A little bit of infrared for this next one, and we just need to match the molecules up to the spectra. Probably the first one that I would be looking at, so I would decide, so for E we've got a carboxylic acid, so this will have the 2 groups expected in a carboxylic acid, and so there's the broad OH for a carboxylic acid, as well as the carbonyl. So I'm pretty confident that that one is E, and then we've just got the other 2 to look at. We can see that one of them has the OH for an alcohol and the other one doesn't. So the carbon-carbon double bonds and the carbon-oxygen double bonds are often quite close to each other, so that would be the last thing that I would be looking at. So I'm happy that G is the alcohol here, which means that I'm left with my ester F, and that's just got the carbonyl group, so FGE. Question 5 proved to be quite a tricky calculation. So this, we can see right from the offset, this is clearly a Q equals MC delta T, and it also involves the enthalpy change. Just remember that the enthalpy change is the energy, which is Q over the amount of moles. So just watch out for that, and we can see that it's an exothermic reaction, so the temperature of the water is going to go up. So where to start with that? So probably what I would look at doing is get the mass of the cyclohexane by doing the subtraction, which gives us 0.63 grams. Let's now work out the moles. So the MR of cyclohexane is 84, which gives us 7.5 times 10 to the minus 3 moles. To work out how much energy is released now, we just want to multiply delta H by the amount of moles. So that's 1,216 times by our 7.5 times 10 to the minus 3. So that's 9.12 kilojoules, or 9,120 joules. So nearly there. We know that Q equals MC delta T. So the bit that we're after, delta T, is Q over MC. So we've got 9,120 over the mass, which is the mass of the water, not the mass of the cyclohexane. So that is 50 times by our specific heat capacity, which is given as 4.18, and so our change in temperature is 43.6. Remember, this is exothermic, so our temperature is going up by 43.6 degrees, and the temperature started at 19.1 degrees, and it's going up by 43.6, so our final temperature is 62.7 degrees C. Of course, the practical side of it, the enthalpy change is a lot less exothermic than expected, so I would imagine that most of you here put something like heat loss to the surroundings, or maybe even incomplete combustion. A little enthalpy cycle for part C, and we're using enthalpies of combustion to solve what is an enthalpy of formation. From your notes, so we've got our combustion products down there, which would be balanced, but that means that to solve this, we've got delta H2 take away delta H3. So for delta H2, we want 6 lots of the enthalpy of combustion of carbon, as well as 6 lots of the enthalpy of combustion of hydrogen. And I got that to be minus 4080, and delta H3, well, that's just going to simply be minus 3920. So delta H1 is minus 4080, take away minus 3920, and that should have come out to be minus 160. Another calculation for question 6. Here we've been asked to work out the minimum volume in centimetres cubed of dichromate needed to oxidise the propan 1-ol. So the place to start with is with the propan 1-ol, and we've got the density, and so density is the mass over the volume. So first of all, we need to work out the mass of the propan 1-ol. So that's the density times the volume, and then we'll divide that by the MR, which is 60, and this will give us the moles of propan 1-ol, which should come out to be 0.08. From the ratio reacting, they're reacting in a 3:1 ratio, so the moles of the dichromate will be a third of that from the 3:1 ratio, which is 0.0267. And then to get the volume of the dichromate, not something that we have to do very often, just remember that concentration is moles over volume, so volume is moles over concentration, which means we've got the 0.0267 over the concentration, which was 0.4, which comes out to be 0.067. That, of course, is in decimeters cubed, so to convert into centimeters cubed, multiply through by 1,000, so we should be getting 67 centimeters cubed. So these questions often cause absolute chaos, so this is where you get to laugh at my diagram. So we want to make the aldehyde, which means we want to set up the distillation equipment rather than a reflux. So I'll attempt to draw some equipment to do a distillation. So the first point is this is looking terrible. but at the minute it's all okay because I've not got any gaps. Now the first thing here is that sometimes we put bungs, etc. on here, so we need to certainly close this off. As long as it's closed off, that's fine. I would probably, I don't think we needed it in this case, include a thermometer. If you are including a thermometer, just make sure that the bulb of the thermometer is next to where your liquid will come off there. Now for the condenser jacket. So again, I'm just going to put this around like so. So it's certainly not a great piece of artwork, thank you very much. So you can see that the water is able to get in and out of my condenser. So here's where the water will go in, so it goes in at the bottom and out here, and then I'll probably just show that that would be filled with water, and then just finish off with a couple of labels, one for the condenser and one for what I can assure you is a flask. Moving on to the Amines question, quite a difficult one this. You can see to start with the balanced equation is worth 2 marks, so we've got an excess of ammonia, so ammonia is going to substitute both of the bromines, which means we're going to get an amino group at either end. I might have drawn my structure out, perhaps skeletally for this diagram. So in kicking the bromines out, so we might be tempted just to put something like HBr, but the other product, remember with the nucleophilic substitution with ammonia, we'll get ammonium bromide. So we just need to balance all this up, which means that we're going to make 2 of those, and we'll need 4 ammonias in the process. Very few students got that right, and also in the real exam. For the mechanism, perhaps an easy mark to start with, as long as we put the lone pair on the ammonia, so we're attacking the delta positive carbon, which is that one there. We now need to show the structure of the intermediate we'd make. So the ammonia has kicked out the bromine, so we've got 1, 2, 3, 4, 5, 6 carbons still there. We've got NH2 there. Remember that nitrogen needs to be positively charged, and I think I would just show one of those hydrogens leaving like that. If you want to bring an ammonia along to remove that, that's fine. It's just another arrow to watch out for. So the secondary amine, which might be formed, so this is a really difficult one. So the clue is that it's cyclic, and basically the amine end with its lone pair can act as the nucleophile. So the nitrogen is now going to be part of the ring. The ring will have 6 carbons. So if you got anywhere near this, that's very well done. So we've got 6 carbons, 1, 2, 3, 4, 5, 6, and then that nitrogen will have a hydrogen attached, so we've made it into a secondary amine. This next part continues to be tricky, so we've got a different synthesis. The clue here is that we're going from 4 carbons to 6 carbons, so there's a trick that we need to become accustomed to, and this is the introduction of a cyanide group to make a nitrile. So we'd use KCN, and this introduces 1 more carbon onto the chain at each end. and the reagent and conditions, so we want aqueous alcohol. And then for stage 2 we're going from the nitrile to the amine, so hopefully we can see that we've bombarded it with hydrogen. So this is the reduction using hydrogen, probably with a nickel catalyst. The comparing base strength question. So 3-aminopentane, as we can see. So we've got this sort of large alkyl group attached to the nitrogen, and this will direct electron density towards the nitrogen, which will make the lone pair more available. So what are the scoring points here? So the alkyl group pushes electrons towards the nitrogen, or you can mention the positive inductive effect, and then the lone pair on the nitrogen, we've got to talk about the nitrogen is more available, or it's better at accepting protons, either of those things. And finally, so justify that there are no chiral carbons in 3-aminopentane. Well, that's the one that comes closest, but there are 2 ethyl groups attached, so we could talk about that, or we could just say that there isn't a carbon attached to 4 different groups. Next question was reasonably well answered. So it's the mechanism of a carbonyl with cyanide again. So we just need to know this. This is nucleophilic addition. Nucleophilic because we're going to be attacking the electropositive carbon, and addition because the double bond is going to open up and we're going to add across there. Part B, fairly standard to start with. So the name of the type of mixture, so equal amount of the isomers. So this is a racemic mixture. And how is it that we get an equal amount? So this is the fact that the carbonyl group is planar, and attack from either side is equally as likely. We then want to do the 3D representations of our molecule. So we've got 2-hydroxypropane nitrile. So there's propane nitrile, and so 2-hydroxy will be like that. So it's important that we get the right molecule to start with. So we can see that our chiral carbon is there. So what I would normally do is draw my 2 mirrored tetrahedra to start with. So make sure that they look something along those lines, and then just pop the groups in. So we've got the methyl group. These can go anywhere that you want. I've got the OH group. Make sure that when you do it in the mirror it becomes HO. And we've also got our CN, as well as finally my hydrogen. In this next one, we're still on with the 2-hydroxypropane nitrile, and it's asking us how we can make this alkene from our 2-hydroxypropane nitrile. Hopefully that we can see that we're losing water to make the carbon-carbon double bond, so we want to dehydrate this. So I'd probably be using something like conch sulfuric or conch phosphoric, and the conditions that they were after, heat, on the mark scheme it says 170 degrees. Here it's after a section of the polymer showing 3 repeat units. Well, to get one section of the polymer, what I would tend to do is draw my alkene out, and then we want to just lose the double bond and then extend the carbon chain. So that shows one repeat unit. So there's a second, and there's a third. On to the last question now. So we've got this synthesis, which looks quite scary to start with. So lots of benzene, lots of reactions going on. For part A, all we want to do is look at the reduction of this. So we've got the nitro group becoming the amine, which means that our other product will be water, and for one nitro group we have 2 waters, and that means that 6 hydrogens were needed in the first stage. The next one, so we've got the acyl chloride versus the acid anhydride, quite a common practical question. So why ethanoyl chloride is not used in the industrial synthesis. So several things that you could write here. Safe one is that it's more corrosive. You might have also gone things for it forms HCl fumes, or it's vulnerable to hydrolysis, or it's dangerous to use. You could have said the ethanoyl chloride is more expensive, reacts violently. So the final mechanism is the nucleophilic addition elimination, and we've been asked to complete the mechanism. So I'm just going to focus on the carbon that's being attacked. So I'm going to start off with that. We can see that the carbon-oxygen double bond has broken to make a single bond. The chlorine's not gone anywhere. The methyl's not gone anywhere. And then the nitrogen is, as well as being bonded to the R group, it's bonded to 2 hydrogens. No marks just yet. So the oxygen became negatively charged, the nitrogen became positively charged, and then they'll be looking. So we've now got a mark for the intermediate, and we just have 3 arrows to put on. So we're reforming the double bond, we're kicking the chlorine out, and then we want to lose one of these hydrogens. So I'm going to do that one with the electrons going back to the nitrogen. We didn't need to show the product. And the last point here, so another aromatic product that was formed in step 3. So going back to step 3 and remembering in step 3 we probably reacted the amine group with the carboxylic acid or an acyl chloride to make the amide group. Well, we could just have as easily have reacted the OH group with that to make an ester. So that is one possible product, or it could have we could have got the acylation on both groups. So that was another possible correct answer.